What's the linearization? It's going to be a tangent line like that. So when you hear this, you go, what is this again? It's a tangent line. It's going to be a tangent line drawn to that curve at what value? X equal to 9. And you already know how to do that. But that's what we're going to do. We are going to draw a tangent line to the curve y equal to square root of x at x equal to 9. And we'll call it the linearization. Okay? So, let's draw a picture. Let's just get an idea of what this looks like. It's always nice to see this. Doesn't the calculator do this too? Yeah. So if you want to look in your calculator, you can too. Here we go. All right, what's the square root function look like? Oh, good job. He goes, ooh, like that? Yep, you too. Everyone else? You're like, that's good. Just goes like that. Just be shooting off like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. But how high will it get at 9?
3.
So I'll just go like that. Stop. That curve keeps going. Whoop. And that's the point 9 comma.
3.
Oh, let me go to you, Caleb. Look, I'm like, all right, they told me 9, but I'd like to know the y value. So I'm going to take the 9 and substitute it into the original, right? Into the original function. Square root of 9 is a 3. And then you and I are going to find this yellow line. Oh. There it goes. You go, what is that thing? I'll tell you, that's L of x. The tangent line approximation to that curve at the value we mentioned. We're going to find L of x. All right. How do we do this? I want to start with point slope form. All right, so I'm changing the color. I'm going to make sure that color. This line is y minus y sub 1 equals m times x minus x sub 1. That's that yellow line. That's the tangent line. Right there. That's the tangent line I'm looking for. I think in my last step, I'll write L of x. Does that sound good, everyone? I'll wait till the end, I'll call it L of x. It's the y I'm going to call L of x. That y right there, I'll call L of x. Now I get to put the point in. That's a 3. There's m. That's a 9. So far, so good?
Mm-hmm.
Now you all have been great with this, especially from grading the last test. This thing. How do we find it? It's the derivative, right? Everyone agree? It's the derivative. So that's f prime of x. And we get f prime of x. What's the derivative of that?
1 over, there you go.
Man, some of you just have that thing memorized now. But when we did do power rule, right? If you have to take a second to go, okay, that was x, right, Amber? X to the 1/2. We took the half in front, then we decreased it by what? By 1. Do you want to see that? I'll do it.
Sure.
Just, oh, I sure will. This, it comes up so often, you might even find yourself going, I'm just going to remember that. I'm just going to remember that that's it. But what happens is, we're doing power rule on that thing. You go, all right, we had x to the 1/2. There's that. You go, what's that prime? He said, well, a half in front, then we decreased it by what?
By 1.
But then, I could take that down here. But then that means I could put a what? Hat on that thing.
Yeah.
But some of you might have been like, I've already seen this 10 times. I may start just memorizing this thing. It's up to you though, Amber. We can always roll through power rule, right? True?
Wait, but it was just m though.
That's right. That's going to be the slope. That will be, the derivative will be that m. But, I'm not going to shove all that there. Because I'm going to evaluate this at what value.
No.
We're going to put a number there. We're going to find the actual slope of that curve, that tangent. So you're like, okay, here, I'm just going to drop a little line here. At what x value? You'll have to call it a, all right, at x equal to 9. And what's 1 over 2 square root of 9? What do you get?
1/6.
1/6? Okay. So that's 1/6. Get that out of the way. We found it. You're a 6th. You're 1/6. So this is really it. But the only thing is, when you talk about it as a linearization, L of x is a linearization, the linear approximation, we solve for y now. So in this case, we will isolate y. So can you help me do that?
Yeah, sure. Y equals
Want to
2.
distribute first or add the 3 first? It's up to you.
Distributed.
Distribute first, okay. I get 1/6 x minus 9/6. Want to reduce 9/6? 3/2.
3/2.
1 minus 3 equals 1/6 x minus 3/2. There, I like that, looks better. Now, how do you get that minus 3 off that side?
Multiply by 3.
Add.
Oh, add and multiply.
That's what he meant. That's what he meant, right? And what's negative 1.5 add 3?
3/2.
Yeah, I think I'll write it as a decimal if you don't mind.
1.5.
Sometimes 3/2 looks weird, students, so I'll write it as a 1.5. Here it is. Y is 1/6 x plus 1.5. The calculator shows this, if you recall, except the calculator might say 1.500000009. Right? Now finally, look what I'm going to do. That's all there. That's my linearization. This is the answer. This is what they're asking for. You got, what are you asking? Find a linearization. Find a limit. That's the linear approximation to that curve at that point. Yeah, you go, tangent line. You know, what's the need for this? I think they really kind of see a need for this with this math problem, and we're going to have to back up like 100 years. Okay, so we back up, that'd be what year, 1915? So back up to 1915, and then when someone said they want you to estimate the square root of 10. Okay? Use this linearization now. They go, hey, do you know what the square root of 10 is? Well, in your head, you know it's just a little higher than what? 3? But I'm telling you, isn't 10 really close to a what? 9. So I want you to look at this image. The square root of 10 would be right on that curve. Does everyone agree? But if we use this linearization, we're going to be a hair above it. We're going to be very close. Do y'all see that? Everyone see that? We'll be really close. So what we'll do is, we're going to use, we'll make this part big. Use your own linearization to estimate the value of the square root of 10. So don't give me the exact answer to square root of 10 on the calculator. We're going to use this linearization. Okay?
But would they have the same value because we took x as 9 over here? Would they
That's
be-
right. This is what's neat. So what we're going to do when we do this, everyone, to answer that question, if we're going to use our linearization, we're talking about, we're using that yellow line here, right?
Uh-huh.
So we're going to use this equation. But go back, it's 19 what?
15.
Oh, it's 1950. There's no calculator. Like, I don't even have any tables near me. But what we're going to do is you and I can see this image. We know calculus. We know that's the square root of x curve. And we know we've got a straight line here. And we know 10 is very close. So all we're going to do is, we're not going to plug square root of 10 in here. We're just simply going to plug in what number here?
10.
Yeah, so look at this. You and I are just going to plug in the number 10 into our equation. It should give us a number that's very close to what? Whatever the square root of 10 is. Does that make sense?
Mm-hmm.
So when this is asked, use your linearization to estimate square root of 10. We're not throwing square root of 10 in here. We're just throwing in what? The value of 10. Go ahead, Josephine.
Could you do part A, but just do A equals 10 instead of A equals 9?
Nope, wouldn't work. Good question. Because we got to make the tangent. We used the tangent line approximation at a number you and I were familiar with. And I think to really understand the problem, Josephine, back it up 100 years. We didn't know what the square root of 10 was exactly at. You know, no calculator. Hey, what's exactly the square root of 10? 5 decimal places. What is it?
3 point something.
Right? And you don't know it, true? So that's why, I mean, that's really, you go, okay, so when this problem was posed to us, here it is, and it was given to us, they used a number that we knew we could exactly get from our knowledge. But then we'll use it to estimate some kind of goofy number that we wouldn't know. You go, well, I don't see no value to this, because now it's 2015, I can just hit this on a what? The calculator? But I just get a sense of what linearization is all about. We back it up 100 years, we're like, okay. You know what's gonna be neat? Watch how accurate our answer is. We're gonna see how accurate. So we're gonna plug in what number into this? So look what we're gonna write here. You're gonna just go L of 10. That's what you're finding. I should put it in yellow. Here. You're gonna find not L of square root of 10, but L of
10.
And I hope this image helps you see it. Look, it's like, it's gonna be like, yeah, it should be really close to what it approximately is. And then afterwards, we can check how much the error is. Like, we'll see, we'll be accurate, I bet, to at least one decimal place. If some of you in your head going, it's probably 3.1, or, I don't know, maybe it's 3.2, right? Maybe it's 3.01, we'll see. All right, plug it in there. See, it's year 1915, we don't have a calculator, you and I can do this math. Everyone, what's 10 over 6?
0.167 or something like
Yeah, 1.666, right?
that. Yeah.
1.6 repeating. 1.6, because it's 5/3, everyone, right? We know that. 1.6666. All right, what's a 1.6666666 plus a 1.5?
3.1 some.
Yeah, what would happen to that? I want to think about it. You got 1.666 and then you add a 1.5. 3.1 and then a bunch of what?
3.166.
So I'm going to do this. Put a line over it. Can you write that as a fraction? Of course you can. But to really see the meaning behind this, I want someone now to hit the square root of 10 on a calculator. Let's see how close we are. This is our answer. Here it is. This is the answer.
Yeah, 3.162.
3.162. How many places were we accurate to?
2.
We're accurate to 2 decimal places by this technique. Isn't that cool? But do you all understand? I didn't use number like 13, because if x equal to 13, what would happen between the distance between the curve and the line?
Higher.
Yeah, it would have spread apart and it wouldn't have been as close. Does that make sense? So this is called the linear approximation or linearization. When you're in, who's going to Calc 3 eventually? All right, Calc 3, it'll be 3-dimensional and you'll have a surface. So think of like a sphere. And you'll get a tangent plane to the sphere. All right, and then what can you do there? You can find what's called a tangent plane approximation. Cool? And you go, oh my gosh, it's going to be so confusing. No, it's going to look just like this thing. It's going to look just like this right here.
It has to be in slope form.
Oh, slope-intercept form. Yep. That's exactly what it is. Hey, if you notice here, this is just like what? L of x was, what was that number there? F prime of what? That was just F prime of x times the x, wasn't it?
Mm-hmm.
Plus that value there. But isn't that cool? I mean, when you calculate, you do these, it'll be called a tangent plane approximation. But they still call it a linearization. You go, it's a plane, I know. You'll do a tangent plane to a sphere. And is there application of this? I think you could see the meaning more in Calc 3 because you got to think of something multivariable. So when think about like, you know, in like the past couple days, just knowing the temperature, does that really tell you how ridiculously it feels outside? No. What else affects it? You got the temperature and what?
Humidity.
Humidity, and that's multivariable. So you got humidity working, then you got what it really feels like, right? Actual temperature, it says 82 degrees, but the humidity is 80%. So what it feels like 97.
Mm-hmm.
And that's what I mean. You got this multivariable function. You got two things going on, but you can do stuff like this to approximate what the temperature would feel like. Cool. So that's where we're going with that. But any questions on this? Cool. So in the end, not too bad. Isn't it something you go, keep it simple. What do you end up doing when they ask you to do this? You're just making a what? A tangent line. We just put it, like you said, in slope-intercept form. We solve for y. And we can call y L of x. The only thing is when they do this thing, make sure you don't plug square root of 10 there. You're just plugging in the what? The 10. You're just going, oh, what do you use? Yeah. All right. That's it. Ready for hyperbolic? sure gonna raise? Everyone's super job, but it is interesting. We're in Calc what?
1.
And here's a linearization. And when you, okay, if I use x naught and y naught rather than point x1, y1.
Mhm.
And then we solve for what letter?
Y.
Y. But you get to Calc 3, you go, oh gosh, that's gonna be confusing for us. No, you're gonna love it. You just get an extra what?
Z.
Right? And it is. This is what it turns into. This is exactly the formula. Now, I have to put something in front of these. What letter's in front of these?
M.
So when you're in Calc 3, you do what's called partial derivatives. And that's the note that's partial derivative with respect to letter x. And over here, you do the partial derivative with respect to
Letter Y.
But you can tell you like, oh my gosh, it's just an extension of this. And they call that a tangent plane approximation. So you're looking at a tangent plane approximation here. This was a tangent what? Tangent line. Tangent line. I just want to show you that. So you go, oh yeah, Calc 3 is going to be a blast. You'll like it, but you can actually do estimates and approximations. The application though is things like that. You can approximate the temperature of how it feels outside. If you got a table values that you can plug in there for like humidity and some temperatures, etc. All right, hyperbolic functions. Here they are. Now I want to tell you what page they're on. I'll put them on the board. Found they're on page 257. And they're called the hyperbolic functions. Some of these you might make up your own names for.